today's topic is creation of some arithmetic functions using logic gates. So I would like to know how familiar you are with binary numbers. Do you know them? Can you calculate something in binary? For example, if I write 1 0 1 1 0 0 1 1 plus 1 0 0 1 1 1 1 1. Can you add these two numbers in binary? Let's see. So how do we add two binary numbers? Let's say this is A and this is B. Let's calculate what is A plus B. So we will be adding 1 plus 1. How much is it? Actually, yeah, how much is 1 plus 1 is 10. So it's 0 and 1 here. How much is 1 plus 1 plus 1? It's 3. 3 in binary is 1 1. So we have 1 as a result and 1 is the carry. So 0 plus 1 would be 1, but because we have carry, we have to add this one as well. So it is 0 and the carry is 1. And here is the same situation. So it's 0 and carry is 1. 1 plus 1 plus 1 is again 11, I would say incorrectly, but it's, 1 is the result and 1 is carry. And here is 1 plus 1 is 2, which is 1 0. I'll just write it right here. So 0 is 0, 1 is 1, 2 is 1 0, and 3 is 1 1. All of these combinations can be obtained by adding two positions, one position at a time. So 1 plus 0 is again 10, and 1 plus 0 is 1, and the carry is 0, and 0 plus 1 is 0, and carry is 1. And I can write it here in brackets, for example. Okay, so this is how we can add two binary numbers. Now, today's task will be to teach a computer or some hardware, some transistors to do it for us. And you'll be surprised how easy it actually is. So first of all, we need to kind of figure out what exactly we're doing in this addition process. What is it that we're doing? So first of all, how many numbers are we actually adding in each position? Can you write in the chat how many numbers do we add? So initially you would think, oh, we're adding two numbers, A and B. But if you look at it, in the first position, yes, but in all other positions, most of the times, we're actually adding three numbers, right? I made these numbers such that even in the second position, we're already adding three numbers, right? So here we think we are adding two numbers, but let's say that initially we set this carry to 0. So in this case, we're still adding three numbers. So this one is A, this one is B, and the third number is C, carry. It's called carry because it is something that is carried to the next position. Okay, so actually we're adding three numbers. And how many numbers do we get in the result? We added three numbers. How many results do we get? We would think that we're only calculating the result Q. I'm going to call this output Q. Right, so we are only focusing on getting Q. So it would be like we're getting just one number, but in reality, we are getting two numbers, two outputs. So when we add two numbers, we get, actually we add three numbers and we get two results. So one is Q and the second one is carry for the next position. Okay, you're very smart. You're already writing it in the chat. So, let's check out if we can somehow generalize it and maybe use in our advantage. So actually, if we look at this example, we can see a few things. First of all, if we add 3 ones, we will always get 1 and 1 as a result, regardless of the position. So we can expand this thing to actually indefinite number of bits to both sides, because it doesn't matter in which position we have 1, 1, 1 here or here. In both cases, we will get 1 as the result and 1 for the next carry here and here as well. So, it's a pretty basic thing. Yeah, so I can write a truth table which has 3 inputs, A, B, and carry, and we will call it carry in, and we will have 2 outputs, carry out and Q in black. So we have inputs A, B, and carry, and I'll call it carry in because that's what we put into this addition. And the result will be Q and carry out, or carry for the next position. How many combinations do we have with these inputs? So we have the following combinations, 8. So A can be 0, 1, 0, 1, 0, 1, and 0, 1. To get it systematic, I'm gonna change the first input on every position, the next one every 2 positions, 0, 0, 1, 1, 0, 0, 1, 1. This is a systematic way to fill these truth tables so that we have all the possible combinations of A, B, and C in here, not randomly, but in some systematic way. Carry in is 0, 0, 0, 0, 1, 1, 1, and 1, like this. So these are all of the combinations of A, B, and C in their values, all of the possible values are in this table. And as I told you, if we're adding all ones here or in other position, it doesn't matter. So these are kind of standalone things. Okay. Now let's fill in this truth table with values. Pretty simple. So what happens if we add 0 plus 0 plus 0? The result will, of course, be 0, and also the carry for next position will be 0. If we add 1 plus 0 plus 0, what do we get? We get 1, and the carry for the next position is 0. If we add 0 plus 1 plus 0, the result is also 1, and carry for the next position is 0. We don't have overflow. Next, what happens if we add 1 plus 1 plus 0? So 1 plus 1 is 10, right? So the Q is 0, but the carry for the next position is 1, right? Do we have such situation here? Here, 1 plus 1 plus 0, we got 0, and the carry for next position was 1. So next A is 0, B is 0, carry in is 1, 0 plus 0 plus 1 from the previous result is 1, and carry for the next position 0. And A, 1 plus 0 plus 1 is 10, and 0 plus 1 plus 1 is 10, and 1 plus 1 plus 1 is the result bit is 1, and also carry for the next position is 1. This, for example, this case, 1 plus 1 plus 1 is 3, which looks like 11. So we have 1 in this position and 1 in the next position. Okay, so this is a truth table. This is what it's called. Truth table for some operation. Okay. Now I will show you a system. Maybe you haven't studied it. People who study electronics in Riga Technical University, they actually have studied this system in something like first year of their studies, which is the system of how we transfer a logic table to transistors. Of course, they also didn't remember most of the part, but at least they kind of knew what I was talking about. Maybe most of you see this for the first time, but I'll show you how it's done and maybe you'll understand it. So if we want to teach transistors to do something that we can describe with a truth table, then we do this 3-step process. First one was to fill the truth table, fill out all A, B, and carry in combinations in the table and calculate the outputs. The second step is optimization. So first we optimize for Q, and it's done using these Carno Maps. Maybe you've heard about them, but Carno Maps work in the following way. We make this 2x2 matrix. Sorry, 4x2. So actually here we will have something like this. And we fill this table in a special way. Fortunately, we have only 3 inputs, so it's not going to be that complicated, but the first 2 inputs we will combine in a combination A times B, something like that, or A and B. And they will go in this direction, and down we will have only the carry in. If we had more inputs, then they would be like 2 in the top and 2 in the vertical axis and so on, but in this case it's pretty simple. So carry in can be 0 or 1. So this is the these 2 rows, and in the columns we write combinations of A and B, but with a small catch that the next position differs from the previous position only by 1 bit. So if I write in the first column 0, 0, then the next column can only change one of these bits. So either we change A or B. So for example, I'm going to change this bit. So the next column will only have 1, 0, and the next position again can only change one of these 2 bits. Because we previously changed A, now we will change B. So here I write 1, 1. I could only change from 0 to 1. And in the last position, we write again combination of A and B, where we only change 1 bit. And because 1, 0 already was used, so here I'll write 0, 1. This is what this guy, Carno, decided would be a correct thing to do to optimize this. And now, so the second way to fill this table is just to memorize the combinations that we write 0, 0, 1, 0, 1, 1, 0, 1. That's all. And in for carry, it's only 0 and 1. And now we fill this table with Q values for all of these combinations. So we make this table only for Q. So when A, B, and C are all zeros, the result of Q was 0, so I write it here. When carry in was 0, so we will now fix on these first 4 lines. I'll write it like this. So when carry is 0, when A and B are also zeros, the result is 0. The Q result is 0. When A is 1 and B is 0, the result was 1. So here is 1. When A and B both are 1s, so it's this line, the result is 0. So 0 goes here. But when A is 0 and B is 1, the result is 1. So this table entry is like this. And the next line is for these values. So when carry is 1, if A and B are both zeros, the result is still 1. 0 and 0 and 1 is 1. Then if A and B is 1 and 0, then the result is 0. When A and B are 1 and 1, this is the last line, the result is 1. And when A and B are 0, 1, and carry is 1, then the result is 0. So it's like this. And in this case, unfortunately, by the laws of Carno, there's nothing to optimize, because Carno says that if you have 2 1s or 2 zeros side by side, you can unite them and one of the bits cancels out. In this case, no 2 1s or zeros are side by side, so there's nothing to optimize. So the second step to draw Carno map, we kind of didn't accomplish anything, so we moved to the third step, which is writing the general equation for this map. So step 3 is writing an equation for the map with all optimizations taken into account if they exist. So Q is equal to, and now there are 2 ways to write the general equation. One is to write for 1s and one is to write for zeros. Maybe for sharpening our minds, we could try to write both ways. Easiest one for me, for example, is writing for all 1s. So to get 1, we can add 1s. I'll write it somewhere in the side. So let's say, how do we get 1? 1 is equal only 1 times 1 times 1 and so on times 1. If any of these 1s would be 0, the result would be 0 immediately. So you get 1 only by multiplying all 1s. And the second way you can get 1, if you add 1 plus 0 plus 1 and so on, plus 0, any number of 1s and zeros, if at least one of the terms is 1, the result will always be 1. So we can write the result as sum of multiplications of 1s, and it is done in the following way. I will even use different colors so we understand which term comes from where. So first I'll use this blue color and I'll write a term for this piece of 1. To get 1, we need all of these bits to be equal to 1, but these A and B are not equal to 1, they're 0. So if we wrote A times B times carry in, well, we wouldn't get this one. But if we invert A and B, then this thing is equal to this one, because A with inversion is, in this case, it's 0, but if we change it to the opposite, it would turn to 1. B in this position is 0, but if we flip it, it becomes 1. Carry in is already 1, so this term for this 1 will be 0 inverted times 0 inverted times 1 is equal to 1 times 1 times 1 is equal to 1. And this is how we get this piece of 1. Okay, so this is the system, how it's done. If you need 1, you need to have all terms equal to 1 in multiplication, and you obtain them equal to 1 by inverting those bits. So to get this one, we take A inverted times B inverted times C without inversion because it's already 1, and you get this term. Next term, I'll write plus, and I'll change the color to, for example, this green. Next, I'll write term for this one. So in this case, A is 1 already, so I just write A times. Next is B. B is 0, so to get this one, we need to flip the B to the opposite value. So I write B with inversion. This stripe above the letter means inverted to the opposite, flipped bit, times, and C is also 0, so we need to change it also to 1 to get this one. So I write C carry in also inverted, and this is this one. Plus, then I'll change to something like brown, this one. So here A and B are both 1s, and the C is also 1. So this is the term here. Plus, in pink, this one. So here A is 0, so we need to change that. A inverted times B is 1, so B is as is, and carry in is 0, so it's also inverted. Okay. So, and that's it. We wrote this equation for all 1s. Okay. And I can guarantee you that if we go through all of A, B, and C combinations, for all combinations that are equal to 0, none of these terms will be equal to 1. And for each one of these terms will be equal to 1, giving the 1 as the result. You know, you can try out other combinations, for example, 0, 0, and 0. If we write 0, 0, and 0 here, then it will change to 1, 1, 0, but the result will still be 0, so we don't get false 1 here, for example. For the next position, the same, 0, 0, 0. Again, we get 0, 1, 1, but it's because of this 0, the multiplication will still be equal to 0, so no mistake here. 0 times 0 times 0 is 0, and 0 times 0, 0, 0, 0 here. We change this one to 1, this one to 1, but because B stays 0, this is also 0. So for example, by using the system, we don't get false 1s. So if A, B, and C are all 0s, then this equation guarantees that none of these terms is equal to 1, so we don't get false 1. And so on. It's true for all positions. All positions where we see 0, this equation will have 0 in the multiplication of all of these parts, and we will get 0. And in case of ones, one of the terms will be equal to 1, and we will get the result equal to 1. So again, no lost ones and no false zeros in this method. And the second way to write the equation, I'll write it in, I don't know, this color, for example, here. Q is also equal to, and for Q is equal to, the way it's written is the opposite. We want to get zeros, so we multiply. 0 is equal to 0 times 0 times 1. Anyway, when we multiply some logic levels, only if at least one term is 0, then the result is immediately 0. And if we add, so only if we add all zeros do we get result equal to 0. If one of these terms is 1, then we get 1 automatically. So we would do the opposite of what we did here, and we would yield the same result. Just let's change it to the opposite system. So we will write for zeros by multiplication, by addition. So first term will be, for example, for this 0, 0, 0, 0. So 0 plus 0, sorry, A plus B plus C is the first term. And then times multiplication times, for the next 0, it is A is written directly plus B, sorry, A is inverted to get 0. So A is 1, because we need 0, we need to flip it to 0, so I write it with inversion. B is 0, so I write B as is, and plus carry in this position is 1, so we need 0, so we need to flip it to the opposite level as well. Carry in flipped times, and then this 0 is 1, 1, 0. We need 0, so we need to invert A and B. Carry in is 0, so I write it directly. Times, and the final 0 here, so it's 0, A is 0, so we write it directly. Plus B inverted plus C is 1, so it's inverted as well. 0, 1, 1. Okay. And we would actually get the same result. Okay, if we did it like the opposite way, these two things should be equal. Let's just check it out. So to get 0, any one of these terms has to be equal to 0, and we can only get them equal to 0 if all elements in these brackets are equal to 0. If any one of these is equal to 1, then we fail, we get 1. So let's see, for example, for zeros, we kind of guarantee it. Let's say A is equal to 0, B is equal to 0, C is equal to 0. This one term will be equal to 0. We don't care what the value of other terms is. If we multiply by 0, we just immediately get 0 as the result. So we kind of guarantee these zeros. What about ones? For example, here we have 1, A, B, and carry in. So A is 1, B is 0, carry in is 0. And if we perform these inversions, so here 1 plus 0 plus 0 will be equal to 1. Here A is inverted and carry in is inverted, so we get 0, 0, 1. But the result is still 1, A, B, and carry in. So we invert this bit and this, so it's 0, 1, 0. But if we add them together, we still get 1. And here A, B, and carry in, A is 1, B is flipped, and carry in is flipped. So the result is still 1. And this way, if we multiply 1 times 1 times 1 times 1, we get 1. So with this second method, we still get correct zeros and correct ones in all other cases also. So I just want you to know that there are two ways to proceed. One is to write sum of multiplications for ones or multiplications of sums for zeros. For me, easier for my mind is to use this method. I don't know, it's just simpler for me to write for ones. That's it. So we'll continue this way. So yeah, how many steps did I say we had? We write the truth table, we write Carno Maps, we write the general equation for either ones or zeros, and then finally, we change this equation to Nands and Nors. There is this law, which is called De Morgan's law. I think that's how it's pronounced. Sorry. So De Morgan's law says the following thing. If you have an equation, for example, A times B, what you can do is you can, with inversion above this thing, you can break the line and change the sign. So basically A times B with a stripe above both of them is equal to A inverted plus B inverted. So I broke the line, I changed the sign, and the results will be equal. And the same goes here, A plus B with stripe above, inverted. If I break this line and change the sign, I will get A inverted times B inverted. So basically, this is what this De Morgan guy calculated. You can calculate it on paper. It can be proven just by calculating all combinations. And it's true, and it helps us in the following way. Right now, the way that we wrote this equation, it performs two operations: multiplication, which is and then additions, these pluses, which corresponds to OR. But in previous lesson, we studied that and OR are not optimal solutions because NAND and NOR are simpler, use less transistors, and perform faster. Because we could only get and OR by using NAND and then NOT, and OR we obtained by taking NOR and then putting NOT at the end. So it was like extra work. So we can use these De Morgan laws to change this equation from ands and ors to only NAND in the following way. You will agree with me that if we do double inversion of entire thing, I'll change the color to black. So basically what we do is we write double inversion across all of the equation. let's say we calculate this equation and then we invert it once and then we invert it once more, nothing changes, right? Down. If we have a, logic equation, and we invert it once and then we invert it once more, nothing changes because we changed and then we changed back. What we can do is we break the bottom line in over each of these plus signs. So we have these terms. I will write brackets here. Because multiplication is done first, they are not mandatory, but I optionally choose to write them in this way. And what we did is we have these multiplications in brackets, we do them first, and then we add them, and all of this we do double inversion, and then we break this bottom line above the places where we have pluses. It's completely legal. And what we get is we change the sign from plus to multiplication, and the inversion sign remains over each of these brackets. So I'll rewrite it like this. I will keep the colors so we can follow through. It was light blue. So A inverted times B inverted times carry in brackets, inverted. This is this line. And instead of plus, I write times. Then the next ones, bright green, A times B inverted times carry in inverted, and this part of line, okay? So it's like this, times, and A, B, C, very simple, carry in correctly. And this part of the bottom broken line, and times A inverted, oops, didn't change the colors, but whatever, you will understand, times B times carry in inverted, like this, and the top line stays intact. The top line, okay, I'll draw it black, top line stays where it was. So far, everything correct? I will delete this line so it doesn't bother us. But this is how we changed this equation. The result will stay the same. We just did some manipulations. So what we have in this case is the following. What is something times something times something inverted? We have multiplication, which corresponds to AND operation, and then we have it inverted. How is it called? It is called NAND. So maybe there is something like this. This thing becomes NAND. And we can make it with just a NAND gate with 3 inputs. The next term is again A times B inverted times carry in inverted, and inverted multiplication with inversion at the end is called NAND. So again, the second thing we can also calculate using NAND. And, the same applies for these things as well. And at the end, we have something times something times something times something inverted, which yields us another big NAND. So by doing this mathematical manipulation, we get that we can use only NAND gates to describe this function. Previously, we had to use the same number of and OR. We had 4 AND gates and 1 OR gate. In this case, we have 4 NANDs and 1 NAND, it's 5 NANDs, and it will be faster. So this is what we did. And finally, I will draw a logic circuit, which also performs this action. Where can I do it? I need to erase something a little bit. And I will erase, for example, these things. No, not important. Not important. This one, not important. And this one also. So, and what basically we can do is we see the following thing. We have A's and A's with inversion, B's and B's inverted, carry in and carry in inverted, and then we have something NAND and something NAND again. So the systematic way to construct a circuit that calculates Q for us using these logic gates or these transistors is the following. So we have input A, B, and carry in. And we will just make a line for A. You know, all of this, these are like wires. So this is a line, this is B line, it's like a cable, and this is carry in line, like a cable. And because we're using them also inverted, I will immediately tap into this A bus and make also inverted copy of it. So with NOT gate, I also obtain A inverted. The same goes for B. And the same for C, carry in. Okay, and so these we have kind of set up the lines of A inverted, B inverted, and carry in inverted. And now we can construct the first term. First is A inverted, B inverted, carry in direct, NAND. So NAND gate, as I mentioned, I think in some previous lesson, we draw like this, sorry, is like a big D letter, like this, okay? With a small pimple at the end, because it's the opposite of AND. And for this gate, we have inputs A inverted. Maybe I'll use the colors so we can follow better through. So the first one, I'll draw light blue. Okay, and here we have this gate. So it's A inverted. I take it from here. B is also like this and carry in direct. Next gate is the green one. Bright green. So for it, we have input A. The next one is B inverted, so like this, and carry in inverted, like this. And this gate calculates A times B inverted times carry in inverted, all inverted, so we use this NAND. The third term was brown. So here we have A, B, and carry in directly, A, B, and carry in. And the third one was pink originally. And we use A inverted, B direct, and carry in inverted, like this. And this way we calculate all of these terms. For example, draw around this. this thing goes here. And the last thing that we do is we take all of these 4 chunks and we do another NAND on top, because that's what we do here. It's multiplication inverted, that's NAND with black. So at the end, I use this big NAND, which only takes as inputs all of these guys and produces Q, the result. So far, understand or not? Nothing changed. Okay. So write in the chat, do you understand it or not? Did you follow through? Okay, so I only see yeses. So I'm happy. Now I will save this image. And so this is the way how we construct, how we calculate Q using NAND gates. And now, question to you, knowing from previous lessons how many transistors are in NOT and NAND gates, and how quickly or slowly the signal goes through these gates, can you answer to these 2 questions? First, how many transistors in total do we have in this circuit? How many transistors? You can calculate it in your heads and write in the chat your guesses. And the second question, how long time passes until we change one of the inputs, until the output changes? So we change an input, how many propagation delays do we have to wait until the output changes? You know, we said 1, how many taus we wait until the Q changes it to a new value. So how many transistors do we have in this circuit? I will give you some seconds to calculate. $30 transistors and 2 taus. Good. Some other guesses? 26 trans and 2 taus. Okay, now very good that you calculated these things. Let's check out. I'll tell you my guess. You know, maybe I'm correct, maybe not. But first is these NOT gates. So how many transistors are inside a NOT gate? So it only accepts one input and it either sets output high or low. So it's just 2 transistors here, 2 transistors here, and 2 here, right? And NAND gates. We remember that the NAND gates, each input added 1 transistor in the top shoulder and another one in bottom shoulder. For NANDs and NORs, in one case, the top shoulder was in series and bottom part was in parallel. And in the other gate, they were in parallel in top and in series in bottom, but each input gives 2 transistors. And therefore, because there are 3 inputs, it's 3 times 2 equals 6. So also 6 here and 6 here and 6 here. And this final NAND gate accepts 4 inputs. So it's 4 times 2 transistors equals 8 transistors here. So if you said a smaller number because you remembered visually that NAND gate consists of 4 transistors, For 2 inputs, yes, because 2 inputs each gives 2 transistors and you get 4. But in this case, we have 3 inputs, so it's 6. And then we calculate how much it is in total. So how many transistors? 8 and 2 is 10, 4 and 6 is 10, so it's 20, 20 plus 12, 20 plus 18 is, I think is 38, something like that, right? And about propagation delay, I hope I calculated correctly. So propagation delay is the following. When we change the input, then there is some time for the signal to go through the NOT gate. The NOT gate then gives the new value of NOT input to all of these first level gates at the same time. So all of them change in parallel. So they only add 1 tau, and the output changes after another tau. So it's 3 tau. Okay. Like this. You know, you change A to the opposite. Maybe the inversion of A didn't change anything, but we have to assume the worst case scenario. So input changes, its inverted signal changes, it was 1 tau. Nand gate calculates in another tau, but all of them work in parallel, so they don't add up, they just add just 1 tau. And the final one has to wait for the previous ones, and once they all in parallel calculate after 1 tau, we calculate the result after the third tau, so it's 3 tau, right? And as I mentioned before, we could also build the same queue from and or elements. It would have just been more transistors and 5 taus, because or at least, yeah, 5 taus, because initially we had some terms with inversion, some not, but then we added them, so it's 2 taus, and then we ORed them, it's another 2. So it would have been 5 tau, it would have been much slower. Okay, so this is about Q. I save this picture, and then I will erase a little bit to calculate it for carry out, because right now, after all of this half an hour, we only have calculated half of what we need. But the next calculation will be faster, because I will not go into such detail. So next thing that we do is we will calculate everything for carry out. And the picture I will put in Ortus, so don't worry. You can draw on paper with me. It's very beneficial to you, but if you didn't manage to do the last drawing, then the picture will be in Ortus next to the lecture video. So the next thing that we will do is we will do the same thing for carry out, and maybe we will have some more interesting results. So to do this thing for carry out, basically we already have the truth table, and now we will concentrate on carry out column. And now I'll write carry out values into the truth table in black. So again, the table structure is the same. A and B is the top row. Carry is in the columns 0 and 1. A and B 0, 0, 1, 0, 1, 1, 0, 1. And now let's transfer carry out values. Also, we can do it in our heads. It's not so complicated. So when we added 0, 0, and 0, result was 0. When we added 0, 1, 0, the result was 1, but carry was 0. When we added 2 1s, it was 10, so carry was 1, and the result was 0. When we add 0, 1, and 0, the result was 0. So basically we need 2 or 3 ones to get 1 for carry out. In this case, 0, 0, 1 is just one piece of 1, so it's 0. But here we have 2 ones, here we have 3 ones, and here we have 2 ones. So quickly in the head filling this table, the result will be like this. And you can check it against this table, you will get the same result. So like this. So this was the first step, truth table, then Carno map. And now in the Carno map, we have to try to do optimizations. And in this case, fortunately, we can in the following way. So Carnot says that if you have 2 ones side by side, you can unite them and they will produce a single term. And these 2 ones are also side by side. So I will unite them as well with a different color so we can follow through which one is which. These 2 ones are also side by side, and it's okay that the same one participates in multiple side by side combinations. It's all fine. You just circle around ones that are side by side. And the third one, let's say, is blue, like this, right? So these ones are side by side, we unite them. These ones are also side by side, these also. So we unite them. And what Carnot says is you only have as many terms as you have units. So in this case, although we have 4 ones, we have only 3 units. And so we will only have 3 terms. Q is equal to, and this unification works because of the following thing. If we have a, sorry, I'll write like this, A times B times C plus A inverted times B times C, this A kind of cancels out because of the following thing. I can write it like this, equal to, I take B and C in front of the brackets, so B times C times, and in brackets A plus A inverted. And what is A plus A inverted? Let's say A is 0, then A inverted is 1, so it produces 1. And if A is 1 and A inverted is 0, because it's addition, we again get 1, so we can kind of cancel this thing out and just write equal, because this is equal to 1, we can just write B times C. So if the term, if an element in 2 terms is inverted and not inverted, and the other ones are the same, then this thing cancels out and we can just throw it away. And the same happens here. So A, for example, for the orange part, so A times B times carry in this position carry is 0, here carry is 1, but regardless of carry in, the result is 1, so we can write just directly A times B. We would have written, without unification, we would have written A times B times carry in for this bottom one, plus A times B times carry in inverted for the top one. But as you can see, A times B is the same. Carry in here is not inverted, here is inverted. We would have taken it in front, canceled it out, and we would have gotten A times B anyway. So this thing just allows us to graphically identify these locations where one of the terms is inverted and not inverted in the same time and cancel it out. In this simple case, we could have just seen it and done it on paper, but this Carno map allows us to visually detect such places. And in more complicated truth tables with many more elements, we could much easier spot such things. So in this case, A and B are ones, a carry in is 0 or is 1, so it cancels out, and we just write A times B plus. The second part is, for example, the blue one. In the blue one, carry in is 1, A is 1 and 1, so it didn't change. So I'll write A, which is 1 here and 1 here. B is 0 in one case and 1 in the other case, so it cancels out, because whether we had B equal to 0 or B equal to 1, the result was the same, so we just drop it out and not write. So it will be A times skipped B, and carry in is 1 in both cases, so we write A times carry in plus. And for the green one, in this case, B is 1 and 1, carry in is 1 in both cases, but in this time, A is 1 or 0. Whether A was 1 or 0, the result was still 1, so we drop it out and we use immediately B times carry in. So in this case, because we used Carno Map and we noticed some patterns and we saw that some terms have something the same and something the opposite, we could, following the rules, just drop them out and get this much simpler equation. So it's A times B plus A times carry in plus B times carry in, or and would be more precise way to call it. Okay, so this is what we got. I will delete this thing. And in black, I will do the second part, which is this. So to use, here it's also explicitly visible. Here is and or. We want to use only nands and nors and nots. So I write double inversion on top, and I'm going to break the line here and here. So it will be A. Okay, with the colors A times B inverted, so it will be not A NAND B plus A and carry in inverted, so it's A NAND carry in plus, and in the green, B times carry in inverted, so it's NAND. Oh, sorry, and I didn't change the signs. Sorry, this will be multiplication. So times and times. And the black inversion sign on top stays like this. And this is our expression using only NAND. And now inputs, we have A, B, and carry in. And because none of these uses the inverted values, so I'm not even going to draw them, we'll only have A, B, and carry in. So I'm going to skip those. And the next part is the terms. So the orange term is A NAND B. The second one is A and carry in inverted, so it's NAND. And The final one is B and carry in inverted. And finally, this last multiplication and inversion is Nand here. And here Q pops out. Sorry, I will not call it Q. In this case, it's carry out. Okay. Did you understand everything? If yes, then now you can calculate again how many transistors do we need to build this circuit, and how many propagation delays do we wait until the output updates. How many transistors do we need, and what is the propagation delay? So 2 inputs, so it's 2 times 2 transistors. So it's 4. Here it's again 4. Here it's 4 more. And here 3 inputs times 2 transistors per input is 3 times 2 is something like 6. So it's 4 and 6 is 10. And 4 and 4 is 8. So it's 18. And propagation delay, the signal changes. It only goes through one Nand gate, and the second Nand gate each adds 1 tau, so it's 2 tau. 2 taus. Like this. Yes, so those who said 18 transistors and 2 taus, they are correct. We change the input, it goes to all of these Nands at the same time. They change in 1 tau, give the result in carry out, and it's calculated and done. Okay, so this is how we can build something that calculates for us Q and carry out using transistors, okay? Because ultimately these gates are just, you know, simple connection, very, very simple basic connection of transistors. And last week, I think we had this new Apple event. I don't know if you're loving or hating it, but you know, it's interesting from technology point. Those people said that their new processors have something like, you know, 14 billion transistors or something like that. Well, now you know how exactly those transistors are put in there. They're not just randomly thrown into the chip, shaked, and then something pops out. They are basically used to build these logic circuits with Nand gates, and then they calculate something for us, whether it's adding 2 numbers or it's maybe some video compression or decompression. It's all done this way. And so many algorithms are developed in such way that they would be easy to implement in these NAND not NOR gates, so that it will be easier to build them in hardware and have some hardware acceleration. Okay, so this is about calculating Q and carry out. And let's move to the next level. So we generalized our transistor connections to these gates. I didn't draw it using transistors. I could have, it wouldn't be that complicated, but you know, at some point it starts to become all just too much on the screen. So we will generalize these two circuits to some things that we will call 1-bit half adder and carry calculation unit, for example, something like that. And if we put them inside the same block, it will be basically 1-bit adder, 1-bit full adder. So I will take a new page, hopefully like this. And so basically what we do is we introduce a new element, black, like this. This small thing, which will accept two inputs, bit A and bit B, and the third input will be carry in. And as we calculated initially, it's just equal to 0. By default, when we add two numbers, by default, the first carry in is just 0. And this block will produce our output and carry out for the next position. Right? And we will call this thing 1-bit full adder. One-bit full adder because it produces both Q and carry out. So we need to add one position of the bits. We give the carry in, A and B, and it calculates Q and carry out. And as we figured out previously, Q is calculated after 3 tau and carry out is calculated after 2 tau. And basically what people decided to do, and the reason why they basically built this whole thing is they figured out, hey, why don't we take these 1-bit adders, put them side by side, and then we can add two numbers together, instantly. So if we cascade these 1-bit full adders, I think we don't have copy option here. Doesn't work. Select. Okay, I'll have to draw it with my hands. So people can just take multiple, build and use multiple of these 1-bit full adders side by side like this, and have an n-bit adder. One, two, three, four, 5, 6, 7, and 8. Basically, just copy these things. And instead of just A and B, we will call these bits 0. Here we will have number A bit 1, A and B bits 2, and so on. So A and B. Like this. And then the carry is basically given from the previous position to the next so that the next bit can be calculated. And we get Q0, Q1, this thing produces the carry for the next position. Once the carry is received, A and B are already in the position. So this thing calculates Q2 and carry for the next position. Then it calculates Q3 and carry for next position, and so on. And after addition, we get this carry out, kind of free carry out, which is in computers not used, but stored. Okay, so basically we have these 1-bit full adders chained in this way, so that we give 2 8-bit numbers, and it immediately calculates us the result. Do you understand this concept? You can write in chat, yeah, it's simple, or I don't really get it. It's simple, you say. Okay, you're smart people. So this thing is called, for example, 8-bit ripple adder. And yeah, it has a special name. Now, my question to you is, how many taus do we have to wait until we get the last Q? After how many taus do we get the last Q stable? We give A, B, and carry in. We just say calculate it. And after how long time do we get the Q7? How many taus could it be? And after how many taus do we get carry out? So this method to create 8-bit adders was, of course, initially used, and it's very good. It works. But the problem with this 8-bit triple adder is that to calculate the next position, you have to wait for the previous positions carry out, right? So this works, this is good, and the first processors did it exactly this way. But, you know, to calculate next Q, you have to wait for the previous carry out. This thing calculates it in 2 taus. So the next position can only start calculating after 2 taus, the one after that after 4 taus, the next one after 6 taus, and so on. So generally speaking, this carry for the last position is calculated after 2, 4, 6, 8, 10, 12, 14 taus. So this carry out is calculated after 16 taus, and Q7 is 14 plus 3, so it's 17 taus. And generally, we can write it as number of bits minus 1 times 2 plus 3, and for carry out is number of bits times 2. And that's all. So this triple adder is, you know, simple and good, but it's a little bit slow. For 8-bit systems, doesn't matter. Remember, the first general purpose processors that were built, I think they were built by Intel or by Motorola. They were actually 4-bit processors. So they had only a few legs. You selected what operation you wanted to do. You gave the numbers, 4-bit numbers, and it calculated the result, but it was 4 bits. So initially it wasn't a problem. But in today's computers, we have, you know, 64-bit architecture. What does it mean, a 64-bit architecture? Generally, it means how wide your arithmetic logic unit is, or how big numbers it can add in one clock cycle, which basically is how wide is the addition part of the processor. And I can just tell you right away, a 64-bit processor, of course, has a 64-bit adder, which basically consists of 64 one-bit adders chained in series, built in this way. But the problem would be that for 64-bit architecture, calculating the result would take 64 minus 163 times 2, something like 124, plus 3, 127 clock cycle, 127 taus, right? So it's kind of slow, right? So if you kind of think about it, carry out is a function of A, B, and carry in, right? The next carry out is a function of A, B, and carry out, but because carry out is a function of A0, B0, and carry in, then if you really think about it, the carry out is not really a function of carry out from previous position, but a function of A1, B1, A0, B0, and carry in. So theoretically, it has to be, we have to be able to calculate it only from A1, B1, A0, B0, and carry in, without this middleman carry out. For the next position, again, maybe with different color, carry out for the third bit is again function of A2, B2, also carry out, but because carry out is calculated from A1, B1, carry out from the previous position, which is calculated from A0, B0, and carry in, we have to be able to immediately somehow calculate carry for the next position, only knowing A2, B2, A1, B1, A0, B0, and carry in, because these middlemen, they are derived from these values anyway, right? So there are two ways to calculate carry out for each position, only from A's, B's, and the first carry in, which we cannot know because it's given to us. And the simplest, most basic thing would be to create a large truth table where we write all possible A and B combinations and carry in combinations. And then we write values for each carry out. Then we draw Carno map for each carry out. And then we construct for each carry out a logic circuit which accepts all bits of A, all bits of B, carry in 0, the first position, and produces us the carry out for each position, right? And we would just copy them. And so it's possible to build something that calculates us all carries only from the inputs without the middleman. And there's also a simplified method called carry propagation or something like that, which produces almost as good results, but with a little less work, because in this case we would have to write truth table for each carry, and each truth table, since we have, for example, 64 inputs, how many combinations would it be? 2 to the power of 64, enormous number of combinations. So mathematicians have figured it out a little bit simpler way to calculate it. So generally, in modern processors, we use something called a Carry Lookahead Unit. Okay, I'll write it here. So it's a logic circuit which calculates each carry only from the inputs. theoretical maximum speed would be 3 tau. If we do this entire hard work of Carno Map and something like that, we can write any, from truth table, we can write any term equal to nands of some combinations of input terms. So generally any expression in binary can be converted to simple NAND with 2 levels and the not in front of it. So theoretical speed is just 3 tau, but since it would be very exhausting, there are carry lookahead units which use some shortcuts and calculate carries in something like 5 tau or 6 tau. But generally, it's much faster than 127 taus for 64-bit processor. So, you just have to remember that modern processors use something called carry lookahead unit. So it's an upgrade to this ripple adder. But maybe, I think that in Logisim, it's possible to build this carry lookahead unit easily for something like 4 bits. And initial 8-bit processors, they build a simple carry lookahead unit for just 4 bits. And then another carry lookahead unit for the next 4 bits. It wasn't as fast as theoretical maximum, but this thing calculated all carries in something like 2 taus, gives the result, and the next one after 2 more, and it's just 8 taus instead of 16 or 17 and so on. So it's possible also to build smaller carry lookahead units for some limited number of carry outs and for carry ins, and just have multiple of them chained. So this is how we build adders from 1-bit adders, and modern days for carries we use carry lookahead unit. And in the cases where we use carry lookahead unit, this part would only calculate queues, so it would be called 1-bit half adder. Half meaning it only calculates queue, not the carry bit. So okay, so I guess that's all for today. This is I try to explain how we build 8-bit adders. The number of adders is equal to the bit number of the architecture. 8-bit processors have 8-bit adders, 64-bit processors have 64-bit adders, and they're basically built from 1-bit adders, which are built from logic gates, which are built from transistors. So actually pretty simple stuff. And just on the final note, if 1-bit full adder is built using 38 transistors plus so each 1-bit full adder uses 38 transistors for Q calculation, plus 18 transistors for carry out calculation. And we have, for example, 8 bits times 8. Then we can calculate, I'll use a calculator to calculate how many transistors we have. So it's 56 per 1-bit full adder times 8 equals to 448 transistors, right? So you see that even one simple adder uses 448 transistors. So when you hear, millions of transistors inside a chip, yeah, it's necessary, it's cool. At the same time, it's not like it's kind of magical number that you reach and everything works better. It's pretty basic actually. Like this. Now save. Okay, and right now, after this lesson, you are actually ready to start doing the labs. So I encourage you to do the lab number 1. It consists of 3 parts, but they're very short and simple. So I think you can do it within 1 hour. You have to install Logisim. It's a special program in which you can do exactly what I was doing here on the whiteboard, except the transistor part. In Logisim, you immediately have these not NAND nor gates and the drawing board, and you can just drag and drop these gates, tell how many inputs you need, and then you just connect them. And you can also simulate the circuit online by changing A, B, and carry in values and check out if the carry out calculates correctly, right? And you can also create sub-circuits. So basically you create, for example, 1-bit full adder from logic gates, and then you tell the program to use it as a building block. And you can, instead of building everything just from NAND, NOT, and NOR, you can drag and drop your custom built building blocks into higher level circuits, and you can easily create such 8-bit adder and test it out. So do the labs 1, part 1, part 2, and part 3 for the next lesson. And then the next lesson, we will check out what more we can do with a simple 8-bit adder. You'll be surprised, actually. So, okay, that's all for today. And now it's time for questions if you have any.